Good day, everyone. I am John Francis de Borja, and together with my team members Noaim ABUBACAR and Carl Amraphel we will be discussing the fundamentals of solar energy. To begin, let us first discuss what is solar energy. The word solar originated from the Latin word solaris, meaning the sun. This means that solar energy is the energy from the sun that is converted into thermal energy or electrical energy. There are two main categories of solar energy, the solar thermal and the solar photovoltaic or the electrical energy as we know it. Now, the energy from the sun is free, yes. However, the capital cost required for harnessing this solar energy is relatively high. But for this lesson, we will only focus on the fundamentals of solar energy. But how does the heat from the sun travel towards the earth? Solar energy reaches the earth by radiation, and to further understand this, let's move on to the elaboration of radiation fundamentals, which will be discussed by Noaim Abubakar.
Thank you, Francis. Now, we will be discussing the fundamentals of radiation. It starts with the concept of electromagnetic waves. The electromagnetic wave or electromagnetic radiation was established by the Scottish mathematician and physicist James Clerk Maxwell in the year 1864. Maxwell believed that accelerated charges or changing electric currents give rise to electric and magnetic fields. Maxwell dubbed the coupling of these intimately related fields as electromagnetic waves or electromagnetic radiation. It is the energy emitted by a matter in the form of moving waves that travel through space at the speed of light. Though electric and magnetic fields oscillate together, they are perpendicular to one another. This results in the electromagnetic wave moving in a direction perpendicular to both of the fields. He then later summarized this relationship in what is now referred to as the famous Maxwell's equations. So how is electromagnetic radiation produced? Electromagnetic radiation is essentially light, which means that they are not created or destroyed, only conserved by absorption or re-emission. When a propagating photon gets absorbed by an electron at a certain energy level, the electron gets excited and then moves to a higher energy level. The energy gap between the electron's current energy level and the higher energy level is equivalent to the energy of the absorbed photon. When the electron gets de-excited back to the lower energy level, it emits the photon since it has to go somewhere else. The process can be represented by the formula delta E is equal to H times V. Delta E is the change in energy, which can be positive or negative, and can be found when an electron emits or absorbs the frequency or wavelength of light when it moves to a different energy level. H stands for the Planck's constant, and the V stands for the frequency. This back and forth movement of an electron then creates electric and magnetic fields, instigating the process of electromagnetic radiation. In the year 1887, German physicist Heinrich Hertz proved the existence of electromagnetic waves, thus validating the formulated theory of electromagnetism. Hertz's experiment consisted of an induction coil and a Leyden jar, which was the original capacitor, to create an electromagnetic wave and a spark between two brass spheres to detect them. He showed the similarity of electromagnetic waves compared to light and heat waves in terms of their nature of vibration and susceptibility to refraction and reflection, thus proving that light and heat are electromagnetic radiations. Since electromagnetic radiation travel in waves, they are characterized by their frequency, wavelength, and speed of propagation in a medium. Frequency refers to the number of wavelengths that pass a certain point in a given length of time. The wavelength is one cycle of a wave, measured as the distance between any two consecutive peaks of a wave. The first equation is used to get the wavelength of a given wave with a unit of hertz. The second equation shows the relationship of the speed of propagation in a medium to the speed of light in a vacuum. It shows that the speed of propagation in a medium is equal to the constant speed of light over the index of refraction of a specific medium. Max Planck was considered as the father of quantum theory. In his theory, there are two claims that must be remembered. The first is that different atoms and molecules produce or absorb energy in discrete quantities only. The smallest amount of energy that can be emitted or absorbed by an electron in the form of electromagnetic radiation is termed as quantum. Second is the energy of the radiation absorbed or emitted is directly proportional to the frequency of the radiation. This is given by the formula h times the frequency, where h is the Planck's constant equivalent to 6.626069 times 10 raised to negative 34 joules second. This shows that the shorter the wavelength, the higher the energy and frequency it carries. This is the reason why we tend to evade gamma rays and X rays as much as possible, since they are destructive to us. Electromagnetic waves travel at the speed of light in a vacuum. They differ in specific range of frequencies, wavelengths, and photon energies. This arrangement of different ranges of frequencies is what we call the electromagnetic spectrum. This consists of 7 subranges that differ in wavelengths, energy, and frequency from one another. First is the radio wave, which is positioned at the farthest right, which has the lowest frequency but has the longest wavelength. Next is the microwave radiation, the infrared radiation, the visible light, the ultraviolet or UV rays, the X-rays, and lastly, the gamma rays, which is positioned at the farthest left and has the shortest wavelength but has the highest frequency and energy. These specific waves are used practically every day in various applications such as in telecommunications, Wi-Fi, cooking, weaponry, medical imaging, and treatment of diseases such as cancer. Next is thermal radiation. Thermal radiation pertains to the transfer of thermal energy by waves that travels through the air or even through space. It is one of the three ways that thermal energy can be transferred besides conduction and convection, both of which need matter to transfer energy. When the waves of thermal energy reach an object, they transfer the energy to the object, causing it to warm up. Thermal radiation is continuously emitted by all matter whose temperature is above absolute zero. This includes walls, plants, furniture, and even humans. The heat we experience from the sun or how fire warms anyone that is near them follows the concept of thermal radiation. All electromagnetic radiation is light. Light waves have wavelengths between about 400 and 700 nanometers. Light or the visible spectrum consists of narrow bands of color perceived by our eyes as the rainbow hues of color, ranging from violet, which has 0.4 to 0.44 micrometers, to red, which has 0.63 to 0.76 micrometers wavelengths. Red light has relatively long waves, around 700 nanometers long, and has a frequency of around 400 terahertz. Red photons of light carry about 1.8 electron volts of energy. On the other hand, blue and purple light, which is on the other end, have shorter waves, around 400 nanometers. Shorter waves vibrate at higher frequencies, which in turn give them higher energies, with a frequency closer to 750 terahertz. transmit about 3.1 electron volts of energy. Blackbody radiation pertains to the electromagnetic radiation produced by any heated objects, especially black bodies. Let's take flame as an example. The flame starts at a low temperature with a low frequency emitting red light in the visible range. As the temperature increases, the flame turns white and then blue as it moves across the visible spectrum with an increasing temperature. Also, with each temperature corresponds a new maximum radiance that can be emitted. As the temperature increases, the total radiation emitted also increases due to an increase in the area under the curve. This then leads us to the question, what is a black body? All objects with a temperature above absolute zero emit energy in the form of electromagnetic radiation. Since not all objects have the same material, surface condition, and surface temperature, different bodies may emit different amounts of radiation per unit surface area, even when they are at the same temperature. That is where blackbody enters. A blackbody is an idealized object that absorbs all electromagnetic radiation it comes in contact with. It is a hypothetical object which is a perfect absorber and a perfect emitter of radiation over all wavelengths and directions. A blackbody is said to be a diffuse emitter since it is capable of emitting radiation energy uniformly in all directions. It is important to remember that at a specified temperature and wavelength, no surface can emit more energy than a blackbody. The nearest example of an ideal blackbody is the Ferris blackbody. It is a double-walled evacuated spherical cavity whose inner wall is blackened. The space between the walls is evacuated to prevent the loss of heat by conduction and radiation. There is a fine hole in it. The entire radiations incident upon this hole are absorbed by this blackbody. It is the hole that is to be regarded as a blackbody and not the total enclosure. The emergence of the blackbody gave birth to StefanBoltzmann's law, which states that energy radiated per unit surface area of a black body and unit time is directly proportional to the fourth power of the black body's absolute temperature. It was formulated in 1879 by Austrian physicist Joseph Stefan as a result of his experimental studies. The same law was derived in 1884 by Austrian physicist Ludwig Boltzmann from the thermodynamic considerations. If E is the radiant heat energy emitted from a unit area in 1 second, and T is the absolute temperature in kelvins, then E is equal to sigma times T raised to 4. The Greek letter sigma represents the constant of proportionality, called the Stefan-Boltzmann constant, which has a value of 5.670 times 10 raised to negative 8 watts per meter square Kelvin raised to the 4. The Stefan-Boltzmann law brings forth the total blackbody emissive power, EB, which is the sum of the radiation emitted over all wavelengths. The spectral blackbody emissive power is the amount of radiation energy emitted by a blackbody at a thermodynamic temperature T per unit time, per unit surface area, and per unit wavelength. The term spectral indicates wavelength dependence. The relation for the spectral blackbody emissive power, EB lambda, was developed by Max Planck in 1901 in conjunction with his famous quantum theory. The following relationship between emissive power, temperature, and wavelength is known as Planck's distribution law, given by the formula C1 over lambda raised to 5 bracket exponential parenthesis C2 over lambda t close parenthesis minus 1 bracket, where C1 and C2 are given constants. This relation is valid for a surface in a vacuum or a gas. For other mediums, it needs to be modified by replacing C1 with C1 over n squared, where n is the index of refraction of the medium. For specified temperatures, the variation of the spectral blackbody emissive power with wavelength is depicted in the figure as an example. This graphic representation can be used to make several observations. First, an emitted radiation is a continuous function of wavelength. At any specified temperature, it increases with wavelength, reaches a peak, and then decreases with increasing wavelength. Second, emitted radiation is directly proportional to temperature. At any wavelength, the amount of emitted radiation increases with increasing temperature. Third, as temperature increases, the curves shift from right to the left. The region with shorter wavelength, larger fraction of the radiation is emitted at shorter wavelengths at higher temperatures. And lastly, the radiation emitted by the sun is in the visible spectrum. And lastly, the radiation emitted by the sun is in the visible spectrum. Our solar system sun, which is considered to be a black body, reaches its peak in the visible region of the spectrum, which is 5780 Kelvin or roughly at 5800 Kelvin. As the temperature increases, the peak of the curve in the figure shifts toward shorter wavelengths. The wavelength at which the peak occurs for a specified temperature is given by Wien's displacement law. This law states that when the temperature of a blackbody radiator increases, the overall radiated energy also increases, and the peak of the radiation curve moves to shorter wavelengths. The shift of the peak is a direct consequence of the Planck radiation formula. Here, the product of the peak wavelength and the temperature is found to be a constant, given by the constant of proportionality B, which is equivalent to 2.8978 times 10 raised to negative 3 meters Kelvin. This law was discovered by the German physicist Wilhelm Wien and is proven useful for determining the temperatures of hot radiant objects, such as stars, and indeed for a determination of the temperature of any radiant object whose temperature is far above that of its surroundings. Now, let's have an example problem regarding radiation emission from a black body. Consider a cylindrical body, 30 centimeters in length and 15 centimeters in diameter, at 327 degrees Celsius, suspended in the air. Assuming the body closely approximates a black body, determine A, the rate at which the cylinder emits radiation energy, B, the spectral blackbody emissive power at a wavelength of 2.5 micrometer, and C, determine the wavelength at which the emission of radiation from the filament peaks. Now for the solution. The surface area of the cylindrical body is pi dl plus 2 pi d squared over 4. Substituting the given, it will give us an answer of 0.1767 square meter. The total blackbody emissive power is determined from StefanBoltzmann Law. Sigma multiplied by temperature raised to 4 multiplied by the surface area will give us an answer of 1298 watts. Spectral blackbody emissive power at a wavelength of 2.5 micrometers is determined from Planck's distribution law. Substituting the given and the given constants will lead us to an answer of 262 Watt per meter square micrometer. The wavelength at which the emission of a radiation from the body is maximum is determined from Wien's displacement. Dividing the Wien's constant by the absolute temperature given will give us an answer of 4.83 micrometers. Note that the radiation emitted from the body peaks in the IR region. And now for the next part of our report, I'll pass the floor to John Francis.
Thank you, Noaim. Now, let's dig a little deeper with radiative properties. What do we really mean when we say radiative properties? Radiative properties are the fundamental physical properties that describe the interaction of electromagnetic waves ranging from the ultraviolet to the deep infrared spectral regions with matter. It can be broadly classified into two: the optical radiative properties, or the way that light reacts with matters, and thermal radiative properties, or the way that the heat interact with matters. But why is it important? Well, it is actually critical for proper selection and interpretation of temperature measurement techniques in various industrial processes, as well as its measurement allows us to understand the physical of solids and other states of matter. With that, let's move on to some examples. Materials like metals, woods, and bricks are opaque to thermal radiation. These are also called opaque materials. This means that the thermal radiation is emitted or absorbed within the first few micrometers of the surface. This is considered to be a surface phenomenon. But other materials like glass and water allows visible radiation to penetrate to considerable depth before any significant absorption takes place. These now are called semi-transparent materials. These are no longer considered as surface phenomenon because the entire volume of the material interacts with the radiation. However, when it comes to infrared radiation, water and glass are practically opaque. This suggests that materials can show different behavior at different wavelengths. Now, this is an important aspect in the study of radiative properties like emissivity, absorptivity, reflectivity, and transmissivity of materials. As has been discussed earlier by Mr. Noaim ABUBACAR, blackbody means perfect emitter and absorber of radiation. Therefore, it can serve as a convenient reference in describing the emission and absorption characteristic of real surfaces. As we all know, heat transfer requires medium, yes, either solid or liquid. But when heat is transferred by radiation, no medium is required because thermal radiation covers the range of wavelengths from zero point 0.1 to 100 microns. Radiation travels through the vacuum with the speed of light in the form of electromagnetic waves. The speed of propagation can be described as the product of wavelength and velocity, where the velocity is dependent on the medium of propagation. Now that we all know that, let's move on to emissivity. Radiation emitted by a surface is determined by introducing emissivity, because it is the potential of a surface to emit energy in the form of radiation in comparison to blackbody radiation at the same given temperature. Emissivity ranges from 0 to 1. Emissivity of metals increases with temperature as well with the increase in oxidation. The image at the left shows the typical ranges of emissivity for various materials. As we can see, heavily oxidized metals have emissivities that is almost the same with nonmetals. Emissivity of a given surface is given by the relation of the energy emitted per unit area of a real body over the energy emitted per unit area of a black body. Emissivity is also dependent on the wavelength, temperature, and angle of emission of radiation. The spectral emissivity is given by the equation shown in this slide. By moving on, let us discuss everything around us because everything around us constantly emits radiation. Now, this radiation flux incident from all direction is what we call the irradiation or incident radiation, denoted by the symbol G. There are three responses when an incident radiation hits a surface. First is that it can be reflected by the surface. then or absorbed by the surface or transmitted by the surface. When the irradiation is absorbed, it is due to the absorptivity of the surface that can range from 0 to 1. When the incident radiation is reflected, it is due to the reflectivity of the surface that can also range from 0 to 1. And lastly, when the irradiation is transmitted through a surface, it is due to the transmissivity, which also range from 0 to 1. According to the first law of thermodynamics, the sum of the absorbed, reflected, and transmitted radiation must be equal to the incident radiation. By applying this law, we will arrive with this formula. Now, by dividing each term by G, the equation will become alpha plus P plus tau equals to 1, where alpha is equal to the absorptivity, Phi is equal to the reflectivity, and tau is equal to the transmissivity. For idealized black bodies, since it is a perfect absorber and emitter, no part of the irradiation will reflect nor transmit. However, for opaque surfaces, the irradiation penetrates into the first few micrometers of the surface. Therefore, there will be no transmissivity but only absorption and reflection, which is why our equation becomes absorptivity and reflectivity equals to 1. Absorptivity depends on the temperature of the source where the incident radiation comes from. By looking at the figure on the left, we will see the variation of absorptivity with the temperature of the source of irradiation for various common materials at room temperature. We can see from the figure that the absorptivity of different materials change when the temperature changes. The absorptivity of material may be quite different for radiation originating from sources at different temperature. For example, a house surrounded by buildings and trees are under the heat of the sun is shown in the figure at the right. The absorptivity of the concrete roof of a house is about 0.6 for solar radiation and 0.9 for radiating originating from the surrounding trees and buildings. This shows that the absorptivity is different from different sources with different temperature. According to Gustav Kirchhoff, or the Kirchhoff's law, the emissivity of a surface at a temperature T is equal to its absorptivity for radiation coming from a black body at the same temperature. With this, we can obtain the relationship between emissivity and absorptivity as depicted on the right. Now, let us have one example for emissivity and absorptivity. By the example given, an opaque horizontal plate is well insulated on the edges and the lower surface. The irradiation on the plate is 2500 watt per meter squared, of which 800 is reflected. The plate has a uniform temperature of 700 Kelvin and has an emissive power of 9000. Determine the total emissivity and absorptivity of the plate. Now, to solve this, we first have to determine the total emissivity of the plate, where emissivity is equal to the emissive power over the product of Boltzmann's constant and the fourth power of the temperature in Kelvin. This would be 9000 over Boltzmann constant multiplied by 700 Kelvin raised to the fourth power. Since this is an opaque surface, the formula we will use for absorptivity is 1 minus the reflectivity. To determine the reflectivity, we have to find the ratio between the reflected radiation and the irradiation on the plates, which is 800 over 2500, that will result to 0.320. Now that we have solved for the reflectivity, we can now solve for the total absorptivity of the surface using the formula that we have derived earlier. Absorptivity is equal to 1 minus the reflectivity of 0.320. The total absorptivity is 0.680 of absolute value. Now that we know this, let us now move on to the greenhouse effect. Let's begin with an example. Imagine a car exposed under the extreme heat of the sun. When you get inside the car, it is overwhelmingly hot. It is because the heat is trapped inside the car because of the glass. Now, to further understand this, let us take a look at the transmissivity curve of a glass. As we can see, glass at the thickness encountered in common use transmits over 90% of the radiation in the visible range and is practically opaque to the radiation in the longer wavelength infrared regions of the electromagnetic spectrum. Therefore, glass has transparent window in the wavelength range 0.3 micrometers to 3 micrometers in which over 90% of solar radiation is emitted. What happens is that glass allows the solar radiation to enter but does not allow the infrared radiation from the interior surface to go out. Now, this heating effect, which is due to the non-gray characteristic of glass or clear plastics, is known as the greenhouse effect because it is being used in greenhouses, and by doing this, the plant stays warm even at night or even at winters. As a stereotype, the Earth is said to be hot and getting even hotter due to this greenhouse effect, but the greenhouse effect is actually good. It is the reason why our planet is warm and habitable. It helps in supporting the life here on Earth, and without this greenhouse effect, Earth would be frozen and inhabitable to any creature. Many greenhouse gases include carbon dioxide, water vapor, methane, nitrous dioxide, ozone. Now, these greenhouse gases are the ones responsible for trapping the heat inside the Earth. Yes, that is true. But the only problem is that man-made activities amplifies the greenhouse effect. By voraciously burning of fossil fuels, we emit so much carbon dioxide, which causes the earth to heat up so much than it should be. Now that we know about the greenhouse effect, we can now discuss about solar radiation. For that, allow me to pass the ball to Mr. Carl Amraphel.
Thank you, Mr. Deborah. Moving on to our next topic, I will be discussing about solar radiation. But first, you may be wondering, what is solar radiation? Solar is derived from the Latin word solaris, which means sun, while radiation is the emission of energy as electromagnetic waves. By combining the two words, solar radiation is the electromagnetic radiation emitted by the sun. It provides light and heat for the earth and energy for photosynthesis. This radiant energy is necessary for the metabolism of the environment and its inhabitants. Not all radiation emitted from the sun reaches the Earth's surface. Much of it is absorbed, reflected, or scattered in the atmosphere. At the surface, solar energy can be absorbed directly from the sun, called direct radiation, or from light that has been scattered as it enters the atmosphere, called indirect radiation. Basically, direct radiation reaches the Earth's surface when there is no cloud cover between the sun and the Earth, while cloud cover causes indirect radiation to reach the surface. The Sun is a nearly spherical body that has a diameter of 1.393 times 10 raised to the 9th power meters, a mass of 2 times 10 raised to the 13th power kilograms, and is located at a mean distance of 1.496 times 10 raised to the 11th power meters from the Earth. It emits radiation energy continuously at a rate of 3.8 times 10 raised to the 26th power watts. Less than a billionth of the sun's energy, about 1.7 times 10 raised to the 17th power watts, strikes the Earth, which is sufficient to keep the Earth warm and to maintain life through the photosynthesis process. The energy of the sun is due to the continuous fusion reaction during which two hydrogen atoms fuse to form one atom of helium. Therefore, the sun is essentially a nuclear reactor with temperatures as high as 40 million Kelvin in its core region. Total solar irradiance, also known as the solar constant, is the solar energy reaching the Earth's atmosphere, whose value is 1,373 watts per meter squared. In this diagram, it represents the rate at which solar energy is incident on a surface normal to the sun's rays at the outer edge of the atmosphere when the Earth is at its mean distance from the sun. The value of total solar irradiance can be used to estimate the effective surface temperature of the sun from the requirement that 4 pi L squared times G sub S is equal to 4 pi R squared times sigma, or the StefanBoltzmann constant, times the temperature of the sun raised to 4, where L is the mean distance between the sun's center and the Earth, and R is the radius of the sun. The left-hand side of the equation represents the total solar energy passing through a spherical surface whose radius is the mean Earth to Sun distance, and the right-hand side represents the total energy that leaves the Sun's outer surface. The conservation of energy principle requires that these two quantities should be equal to each other, since the solar energy experiences no attenuation on its way through the vacuum. The effective surface temperature of the Sun is determined from this equation to be T sub sun is equal to 5780 Kelvin. That is, the Sun can be treated as a black body at a temperature of 5780 Kelvin. Now we have here the spectral distribution of solar radiation. So, the spectral distribution of solar radiation on the ground, plotted in the figure, shows that the solar radiation undergoes considerable attenuation as it passes through the atmosphere as a result of absorption and scattering. The several dips in the spectral distribution of radiation on the Earth's surface, as shown in the figure, are due to absorption by the gases oxygen, ozone, water, and carbon dioxide. Absorption by oxygen occurs in a narrow band about 0.76 micrometers. The ozone absorbs UV radiation at wavelengths below 0.3 micrometers almost completely, and radiation in the range of 0.3 to 0.4 micrometers considered. Thus, the ozone layer in the upper regions of the atmosphere protects biological systems on Earth from harmful UV radiation. Also, absorption in the IR region is limited by water vapor and carbon dioxide. The dust particles and other pollutants in the atmosphere also absorb radiation at various wavelengths. Another mechanism that attenuates solar radiation as it passes through the atmosphere is scattering or reflection by air molecules, and the many other kinds of particles such as dust, smog, and water droplets are suspended in the atmosphere. Since scattering is mainly governed by the size of the particle relative to the wavelength of radiation, radiation at wavelengths corresponding to violet and blue colors is scattered the most. This molecular scattering in all directions is what gives the sky its bluish color. The same phenomenon is also responsible for red sunrises and sunsets. Early in the morning and late in the afternoon, the sun rays pass through a greater thickness of the atmosphere than they do at midday, when the sun is at the top. Therefore, the violet and blue colors of the light encounter a greater number of molecules by the time they reach the Earth's surface, and thus a greater fraction of them are scattered as shown in the figure. The solar energy incident on the surface on Earth is considered to consist of direct and diffuse parts. The part of solar radiation that reaches the Earth's surface without being scattered or absorbed by the atmosphere is called direct solar radiation, or G sub capital D. Also, the scattered radiation is assumed to reach the Earth's surface uniformly from all directions and is called diffuse solar radiation, or G sub small letter d. Then the total solar energy incident on the area of horizontal surface on the ground is G sub solar is equal to the direct solar radiation times cosine theta plus diffuse solar radiation, where theta is the angle of incidence of direct solar radiation. The diffuse radiation varies from about 10% of the total radiation on a clear day to nearly 100% on a totally cloudy day. It is found convenient in radiation calculations to treat the atmosphere as a black body at some lower fictitious temperature that emits an equivalent amount of radiation energy. The fictitious temperature is called the effective sky temperature, or T sub sky. Then the radiation emission from the atmosphere to the Earth's surface is expressed as G sub sky is equal to the StefanBoltzmann constant times T sub sky raised to the fourth power. The value of the effective sky temperature depends on the atmospheric conditions. It ranges from about 230 Kelvin for cold, near sky conditions to about 285 Kelvin for warm, cloudy sky conditions. Note that the effective sky temperature does not deviate much from the room temperature. In the light of the Kirchhoff's law, we can take the absorptivity of a surface, which is alpha, to be equal to the epsilon, or its emissivity at room temperature, thus making alpha is equal to E. Then the sky radiation absorbed by a surface can be expressed as sky radiation absorbed is equal to alpha times the effective sky temperature equals alpha times the StefanBoltzmann constant times the temperature of the sky raised to 4 equals epsilon, or the emissivity at room temperature, times the StefanBoltzmann constant multiplied by the temperature of the sky raised to 4. The net rate of radiation heat transferred to a surface exposed to solar and atmospheric radiation is determined from an energy balance as shown in the formula below, where P sub S is the temperature of the surface in Kelvin and the E is its emissivity at room temperature. A positive result for net rate of radiation heat transferred indicates a radiation heat gain by the surface, and a negative result indicates a heat loss. Surfaces are assumed to have two sets of properties, one for solar radiation and another for IR radiation at room temperature. The table shown shows the solar absorptivity and emissivity of some common materials. Surfaces that are intended to collect solar energy, such as the absorber surfaces of solar collectors, are desired to have high solar absorptivity but low emissivity values to maximize the absorption of solar radiation and to minimize the emission of radiation. Surfaces that are intended to remain cool under the sun, such as the outer surfaces of fuel tanks and refrigerator trucks, are desired to have just the opposite properties. Surfaces are often given the desired properties by coating them with thin layers of selective materials. A surface can be kept cool, for example, by simply painting it white. Now we have an example of the calculation of solar constant. So the problem is we must determine the solar constant using the total solar irradiance formula. Take the effective surface temperature of the sun as T sub sun is equal to 5778 Kelvin. So for the solution, it is said that the sun is a nearly spherical body that has a diameter of 1.393 times 10 raised to the 9th power meters and is located at a mean distance of 1.496 times 10 raised to the 11th power meters from the Earth. Also, the effective surface temperature of the sun is 5778 Kelvin. Using the formula, we will now substitute the given values. So we have here 4 pi times 1.496 times 10 raised to the 11th power, which is the mean distance. So g squared times g sub s is equal to 4 pi times 0.5 times 1.393 times 10 raised to the 9th power. So it's also squared. So the reason why the radius is multiplied by 0.5 is because we have a given of diameter. So in order to have the radius, we multiply the given by 0.5. So it is also multiplied to the StefanBoltzmann constant, which is 5.67 times 10 raised to the negative 8 watts per meter squared times Kelvin raised to 4. It is also multiplied to the temperature of the sun, which is 5778 Kelvin raised to the 4th power. So doing this in the calculator, we will now have the answer of G sub S is equal to 1270 watts per meter squared. Next, I will be discussing about solar data. The amount of solar radiation incident on a surface depends on these following factors. First is the orientation of the surface, the latitude, also known as geographic location, elevation of the location or altitude, humidity of air, clearness of the sky, or we can also say local weather, and the time of the day. Now we have here a table that gives the hourly solar radiation incident on various surfaces at 40 degrees latitude by ASHRAE 1993. The values given are the 21st of the month for average days with no clouds. The values can be up to 15% higher at high elevations under very clear skies and up to 30% lower at very humid locations with very dusty industrial atmospheres. Daily totals are obtained using Simpson's rule for integration with 10-minute time intervals. So here are the references used in this presentation. And that is it for our group's presentation about the fundamentals of solar energy. Thank you for listening and have a nice day.